So, good afternoon, everyone. Welcome to the third week of discussion session to this course, Plates and Cells, offered by NPTEL. The course instructor of this course is Professor Sudip Talukdar from IIT Guwahati, and I am your teaching assistant. I am myself Asif Raza. I am a PhD scholar from Department of Civil Engineering from ISC Bangalore. So today we would be discussing questions which are more related to the questions of assignment 1. So I'll be discussing those questions. Some of the questions are exactly the same and some questions are a bit changed so that you get the idea how to solve the first assignment questions. So let's get started. Yeah. So let's start. The first question is in the thin plate bending theory with reference to Cartesian coordinate system xyz, where xy is in the plane of the plate. The first options are sigma y, sigma z and tau xz are assumed to be negligible. Second option is sigma z, tau yz, tau xz are assumed to be negligible. Third option is sigma x, tau xy, tau xz are assumed to be negligible, while the fourth option is tau xy, tau yz, tau xz are assumed to be negligible. So, for a 3D state, a stress tensor is given by sigma x, tau xy, tau xz, tau xy, sigma y, tau yz, tau xz, tau yz, sigma z. So the plate bending theory assumes to be the case. The thin plate bend theory assumes to be the case of plane stress, and our plate is in the xy dimension. So the dimension with respect to the z coordinate would be tending towards 0. That would be neglected. So that these are assumed to 0. So the correct answer would be the second option, sigma xz, tau yz, tau xz are assumed to be negligible. So let's move on to the second question. At a certain point P, the strains in x and y directions of a plate are epsilon x and epsilon y respectively. If E is the modulus of elasticity and Poisson's ratio nu is equal to 0.25, then these are the four options. So what would be the correct solution? So let's find it. So we know that epsilon x is given by sigma x upon E minus nu sigma y upon E. Similarly, epsilon y is given by sigma y upon E minus nu sigma x upon E. Adding these two equations, we get sigma x plus sigma y minus nu sigma x plus sigma y by E. This can be simplified as 1 minus nu sigma x plus sigma y by E. If you see the options, most of them are in terms of sigma x plus sigma y. So we'll take that as sigma x plus sigma y is equal to take this thing, so we'll have E upon 1 minus nu epsilon x plus epsilon y. So this gives us E upon 1 minus nu is given to be 0.25. So this gives us 0.75, then this would be 4E by 3. epsilon x plus epsilon y. Solution. So the correct answer is the option 1. Now let's move on to the third question. So third question is, given the deflection of a thin plate Wxy, E is modulus of elasticity, J is shear modulus, nu is Poisson's ratio of the metal of the plate. The shear stress tau xy developed at depth z, where z is less than or equal to h from the middle surface is. So how to solve this? So we know that tau xy, shear stress tau xy, is given by G gamma xy, where gamma xy is the shear strength developed in the plate, and we have the relation G is equal to 2 1 plus nu, and one more relation we have is gamma xy is equals to minus 2z del square w del y del x, right? So if we substitute these two into this equation, we get tau xy equal to e upon 2 1 plus nu times minus 2z del square w del y del x. So this gives us minus this cancels out, so finally it will give us e z upon 1 plus nu del square w dou y dou x. So this is my answer. So the correct option would be option B. Yeah. So now let's move on to the question number 4. So question number 4 is, at a certain point in a slightly bent steel plate, the curvature in x direction was 0.001 per meter. The curvatures at the same point along a direction 30 degree measured clockwise from the x-axis and 60 degree measured counterclockwise from the x-axis are found to be 0.002 per meter and 0.002 per meter respectively. The radius of curvature of slightly bent plate with respect to y-axis in meter to the nearest integer is. So to solve this, we know one thing is that it's better to use. So we know the sum of curvatures in any two orthogonal directions is constant. We need to say we are given with 1 upon rx equal to 0.001 per meter, right? So we have x-axis, we want to find ry, curvature in y direction. So we have I, we are given a curvature value at a 30 degree measure clockwise, 30 degree measure clockwise, let it assume as capital X, and 60 degree measured counterclockwise. as capital Y. So we see that these two given values are orthogonal to each other. So let us write as, so we are given 1 upon capital R x as 0.002 per meter and capital Ry as also 0.002 per meter. We know with this, using this, we get 1 upon Rx plus 1 upon Ry is equal to 1 upon plus y equals 0.001 plus 1 upon Ry is 0.002 plus 0.002 is 1 upon Ry is 0.004 minus 0.001. It's equal to 3 into 10 to the minus 3 per meter. This gives us Ry is 10 power 3 upon 3 meter. So this will be equal to 333.33 meter. So according to the question, you have to round it off to the nearest integer. So Ry would be equal to 333 meter. So this is my answer. So answer is the radius of curvature slightly bent plate with respect to y-axis is equal to 333 meter. So let's move on to the fifth question. So fifth question says, at a certain point in a thin plate, the normal and shear stress with reference to rectangular coordinate system x and y are given as sigma x is equal to 334 megapascal, sigma y is equal to 166 megapascal, shear stress. So at a certain point in a thin plate, the normal and shear stress with reference to rectangular coordinate system xy are given as sigma x is equal to 334 megapascal, sigma y is equal to 166 megapascal, and shear stress is equal to minus 75 megapascal. If the frame of reference is rotated by 45-degree clockwise about z-axis, the sum of two normal stresses in revised frame of reference in MPa rounded off to nearest integer would be. So we need to find sigma n. We know sigma x dash is equal to sigma x cos square theta plus sigma y sin square theta plus tau xy 2 tau xy sin theta cos theta sigma y prime sigma x cos square theta plus sigma y sin square theta minus 2xy sin theta cos theta. We just need to find the sum of two normal stresses, that means sigma x dash plus sigma y dash, which will give me as sigma x cos square theta okay, I made a mistake here. This is sin square theta cos square theta. So this will be equal to sigma x plus sigma y. We have 334 plus 166. This gives me 500 MPa. So So this is my answer to this. Okay, so let's move on to the sixth question. The sixth question is there is a square plate made of steel with Young's modulus of elasticity as 2 into 10 power 11 Newton per meter square, Poisson's ratio as 0.3, thickness of the plate is 10 mm. It is bent by symmetrically applying couple of magnitude 2000 Newton per meter along its edges. The magnitude of radius of curvature in meter rounded off to the two decimal places is. So this question is talking about there is a couple applied both sides and not. So if you refer the equation number 40 of slide 26 module 1 lecture 3, you'll get the relation as Rx and Ry is equal to T1 plus nu upon m0. So D is our flexural rigidity of the plate, which is given by Eh cube 12 1 minus nu square. So we have the value 2 into 10 power 11, then H is 10 mm. So converting it into a meter, it will be 10 power minus 2 meter. Twelve 1 minus 0.3 whole square. So this gives me 2 into 11 minus 6. This gives me 5. 12 into 1 minus 0.09, 0.81. So value solving this we get 2 12 divided by 0.81 is gives me 2.057 into 10 power 4. Now we have m0 value as 2 into 10 power 3 Newton meter per meter. So Rx would be Rx equal to Ry would be 2.0576 into 10 power 4 1 plus 0.3 upon 2 into 10 power 3. So solve like this. This gives me 13.3744. So we have to round it off to two decimal places. So the correct answer we can reduce it here 13.37 meter. So this is my solution to the sixth question. Now let's move on to the seventh question. So the seventh question is the edge of a plate is oblique to the vertical edge by an angle theta is equal to 30 degree. At a certain point on the edge, the moments are mx is equal to 4 kilonewton per meter, my is equal to 8 kilonewton per meter, and mxy is equal to 2 kilonewton per meter. The moment Mn along the direction of normal to the oblique edge in kilonewton per meter, correct up to second places of decimals is. So to solve this, you can refer to the equation number 24, slide number 13, module 1, lecture 2, where the oblique angle MN is given as mx plus my by 2 plus mx minus my by 2 cos 2 theta plus mxy sin 2 theta. So substituting the values, we'll get 4 plus 8 by 2, 4 minus 8 by 2. This would give me cos 60 degree, and this is sin 60 degree. So yeah, mxy value is 2. Solving 8, 4, 2, 6 minus, this would be 4 minus 4, 2 into 1 by 2 plus 2 into root 3 by 2. So this gives me 6 minus 1 plus 1.73, 6.73 kilo Newton per meter. Sorry, kilo Newton per meter. This is my answer. So this is the answer to this question. You can further find the value of m and t with the formula minus of my minus x my minus x by 2 cos 2 theta minus mxy sin 2 theta. Now the eighth question is, we are given a plate of elliptical boundary that is clamped along the edges. The length of major and minor axes of the ellipse are 2a and 2b. The plate carries a uniformly distributed load Q. The deflected surface is expressed. Okay, so we are given with the deflection profile. Here C is a constant, A is equal to 300 mm, B equal to 100 mm. Thickness of the plate is 6 mm. Modulus of elasticity is 2 into 10 power 5 Newton per mm square. Poisson's ratio is 0.3. The load is 0.6 kilonewton per meter square. So we need to find the maximum deflection in mm, correct, up to third decimal places. So we are given with values E as 2 into 10 power 5 Newton per mm square, H as 6 mm, 6 mm, A as 300 mm, B as 200 mm, Q as 0.6 kilonewton per meter square. So it can be simplified and written as 0.6 into 10 to the minus 3 Newton per mm square. Okay, now so this is the deflected profile. We have the plate equation as del power 4 W equal to Q upon D, right? So this equation also, this should also satisfy the plate equation number 2. So what is this? So this is del power 4 W del x4. Okay, so it can be so this gives me that this will become 2 and So for this we need to find these values. Okay, so let's find it. So we are given with W. So we have W as C x square a square plus y square b square minus 1 whole square. Dou W or dou x would be C times 2 x square a square plus y square by b square minus 1 times 2x by a square, that is 4c x by a square x square by a square plus y square by b square minus 1. Del square W by del x square would be, take a derivative of dou W by dou x, we get 4c by a square x square by a square plus y square by b square minus 1 plus 4cx by a square, and taking a derivative inside, that will give me 2x by a square. So simplifying it, we'll get 4c by a square x square by a square plus y square by b square minus 1 plus so this would be 8c x square by a to the power 4. Now take third derivative, x cube will be what? So third derivative will give me 8c 8 to the power 4 8cx, while this will give me 8cx 8 to the power 4, and fourth derivative will give me 8cx 16cx, so this is 24c 8 to the power 4. Similarly, we can find dou by dou y to the power 4, that will give me 24c b to the power 4. Now we need to find dou y square dou y square dou x square. Need to take a second derivative of x square, so this will be so this is the one. So taking a derivative with respect to y will give me 4c a square, and with that 2 times derivatives. So let's do it step by step. So first derivative with respect to y will give me 8c a square b square y, and finally taking derivative will give me 8c a square b square. Okay, so I don't have this space, I'll just move on to So we have the equation number 3 also. Substituting it will get what? We have this, this and this. So substitute in equation number 3, we get 24c e to the power 4 plus 2 times 8c a square b square plus 24c b to the power 4 is equal to q upon d. So taking c outside, we'll have 24 a to the power 4 plus 16 a square b square plus 24 b to the power 4 equal to q upon d. So let us take this as k. So what will be the value of c? It will be q d k. Okay. So we need to find the maximum deflection first. So maximum deflection would be W max would be what? It will be maximum at the center. So this gives me value of c, which is q upon dk. So what is d? D is the flexural rigidity of the plate, which is EHQ upon 12 1 minus mu square, which is the value 2 into 10 power 5 times H is 6 Q 12 1 minus 0.3 whole square. Let's do this. So this gives me 2 into 6 56 6 into 6 divided by 0.81. So this gives me 4.44 into 10 power 6. And the value of k is 24 upon 8 to the power 4, that is 304 plus 16 300 square 200 square plus 24 200 to the power 4. So this will be equal to 24 divided by 3 to the power 4 10 divided by 36 24 divided by 2 to the 4 16. So this is equals to 2.2407 into 10 to the power minus 8 and substituting the value. So we have D and here. So finally the value of W max would be 0.6 into 10 power minus 3, 4.44 into 10 power 6, and 2.2407 into 10 power minus 8. So this gives me 4.44, 2.6, 10 power minus 3, or J 10 minus 3. This gives me 0.06038 into 10 power minus 3 minus 2 minus 1. So this is equal to 0.0603082, which is equal to, if we up to third decimal places, 0.006 mm. So this is the answer. So this solves the 8th question, and I'll just end this session here. In the upcoming session, I'll try to discuss the assignment problems related to assignment 2, so that you guys have the idea like what went wrong with you guys, like were you able to solve or not. If there are any doubts, you can ask. Hello, is there any doubt? I hope everything is clear. So shall we end the session? Can I get any response?
Yes, sir, we can end the session.
Yeah, okay.
Thank you, sir.
Yeah. Okay, bye. Take care.